It's a pleasure to be here and to tell you about some of the work we've been doing using machine learning in the domain of quantum chemistry and quantum mechanics. So research in my lab really revolves around the question of chemical compound space and how we can explore that space from first principles. So using the laws of physics, quantum mechanics, and statistical mechanics in particular. You might wonder what chemical compound space is. There was a Nature Insight in 2004, which I reference here with multiple noteworthy contributions, reviewing the field rather from a pharmaceutical point of view, but still this number 10 to the 60 was floated in terms of conceivable organic molecules. So this is such a vast number that in 2017 there was another review and this number made it in this graphic here. So you see the bar 10 to the 60. So atoms in the solar system apparently is 10 to the 54. So we don't have enough atoms to even produce the hard drive to store just the list of compounds, not mentioning making them or measuring them. Known data sets of chemical libraries which are experimentally approved is shown here, approved drugs. PubChem and zinc contain, so zinc contains some virtual molecules, and GDB17 is the largest database so far of theoretical, so virtual molecules. So they haven't been made, but we would expect them to be stable. So these are they're encoded as molecular graphs, and that's 160 billion or so molecules. Now, and this is just the organic chemistry, right? So obviously, as you include more elements from the periodic table, this space becomes much bigger. And so we would like to explore and better understand this chemical compound space for various reasons. One is, of course, from a chemistry point of view, we'd like to have a better understanding fundamentally, but also it could be very useful for design purposes, let's say, to discover new materials or molecules. Our work has revolved around that. Here's a paper in 2020, which I think is quite important. We introduce here a dictionary of small fragments, which you can use to then predict larger query compounds that can be composed of these fragments. And you can imagine that as chemical compound space, it is so large, it grows combinatorially due to all the possible ways to combine atoms and functional groups. And so if we have a small dictionary of these fragments that then result in the same combinatorial explosion, you might be able to get away with a much smaller dictionary, right? And so that's I think the key idea behind this paper. And here in this animation, you see the 1,000 smallest fragments you would need for organic chemistry. So it's a 10 by 10 by 10 matrix. So in principle, any organic compound could be composed from any selection of these. So more details are given in this paper here. We also recently wrote some reviews on this topic, so you can find some more information in these references. This is an illustration which we used. It was on the cover of this Nature Chemistry Reviews journal, where we show here what you can see is a molecule like aspirin. And every heavy atom in aspirin, we omitted the hydrogens for clarity. Every heavy atom is a star, and superimposed on the heavy atom is a small other molecule which happens to share the atom, right? And so this is just an illustration of the underlying idea that the individual solutions to Schrödinger's equations for one system are not unrelated from the solutions of another system. Yet the way we traditionally do quantum chemistry is by really starting from scratch every time, right? And so I think we owe it to people like Carr and Parinello, who that this idea that you can also propagate or infer electronic structure solutions from previous solutions. This is not something unreasonable. And so we try to sort of bring this into the domain of changing not only coordinates, but also chemical composition and size and considering more than just the energy, also other properties and so on. Now, we basically pursue two strategies for doing this. One is based on perturbation theory, also known as computational alchemy. This, if you haven't heard about this, it might sound a little bit crazy to you, but actually there's a long tradition in chemistry. It's a smaller and narrow field in theory, but for instance, in molecular dynamics simulation, computational alchemy is quite common. The entire conferences organized on this or issues. In density functional theory, there is, for instance, a paper by E. Bright Wilson from the 60s, where he develops a four-dimensional density functional theory, which includes changes in the nuclear composition. And also already actually Erich Hückel in the early days of quantum chemistry asked this question, what is the first order derivative, or what is the perturbation you would experience in your Hückel solutions as you mutate your carbon atoms towards nitrogen or oxygen. So strictly speaking, the first order term for any such change in coordinates or nuclear charges could be given by the Hermann-Feynman derivative. You can, of course, go higher in order, and then you have higher order perturbation theory, and you can expand your target energy, let's say, in such Taylor expansions in some coupling parameter lambda that gets you from some initial system, some initial Hamiltonian to some final Hamiltonian. Now, in this work with my postdoc Guido von Rudolph, we developed an alchemical perturbation density functional theory, where we showed that you only have these perturbations in the electron density. So it's basically an orbital-free density functional theory, which, as long as the perturbations are relatively small and as long as the series will converge, it's going to be exact, or it converges towards the exact solution. So this perturbation theory basically tells you if you have the solution to a point, right, and you have derivatives, you can expand in this on the surface, on the state, and we would expect a single, just as in perturbation theory, to the state to be smooth. Now, this is not necessarily the case if your perturbation is large and you have some surface crossing, right? Then you would predict solutions for an excited state, but I think that is okay. Now, sort of the complementary view on this would be to use some notion that so suppose you had the solutions of these empty symbols. What is the most likely solution for this filled symbol, right? And that is the Bayesian question, the most probable answer given all these other. And so that is typically what we do when we regress and when we interpolate. And so the natural thing then is to use machine learning for this. So this would be supervised learning, right? We have inputs. Our Hamiltonian is defined by the external potential, which is given by the nuclear charges and their coordinates. And this will produce some solution and some eigenvalue if you solve Schrödinger's equation. So this is the label, and this is the input. And given sufficient examples for a new input, you can systematically, rigorously infer the label, right, without having to solve the differential equation. And so that's of course where the appeal comes from. And so people like Vapnik, Vladimir Vapnik, or others have put this on rigorous footing in terms of statistical learning. Now let me just give a brief example on this perturbational part. Just so that hopefully you see that there's a relationship in compound space. We recently discovered this this relationship. It's we call it alchemical chirality. So if you consider the electron density of benzene, and you would perturb it either to NBBN or to BNNB, these are constitutional isomers, but they by chemical intuition, you would argue they have different bonds, and so they are not necessarily similar in energy. It actually turns out that these two isomers are related to each other. They constitute what we call an alchemical enantiomers. So you can reach them by perturbing benzene, and simply by changing the sign in your perturbational Hamiltonian, you get to either one of those. And as a result, up to third order in the perturbation expansion, your electronic energy between these two systems will be degenerate, and so it's like an alchemical reflection plane, if you wish, and you cannot through rotation or translation superimpose these two compounds. So this is a constraint, right? A relationship in chemical compound space. And so a regression model should find these implicit correlations in the data and then exploit them. So this is, since this talk is only about quantum machine learning and this entire seminar today, so I will not spend more time on this perturbational aspect of our work, but it's intimately linked, of course, and I'll address now some of our more recent quantum machine learning work. Now, before I get there, and also to make the distinction clear to the previous speakers, what we are referring to in terms of quantum machine learning is not using quantum computing, right? So rather, we use this term in the same sense as you would speak about quantum Monte Carlo or quantum molecular dynamics. So meaning that you do something classical to describe a quantum object, right? And so we use classical machine learning, and there's this little 2x2 matrix here from Wikipedia, which also makes this distinction. So our algorithms are not quantum, rather classical machine learning algorithms, but our data is quantum. So we are in this QC box, if you wish. So this acronym, this notation is in line with what is conventionally being done in our community, in the atomistic simulation community. So I think it's okay if there's more than one interpretation of this acronym. You know, there's also density functional theory and discrete Fourier transforms, and so it's not without precedent that an acronym is shared among multiple communities. Now, one important thing also for me is that we would like to distinguish our ways of building these machine learning models from QSPR or QSAR approaches, as they are quite common in cheminformatics and bioinformatics. There's a long tradition for computers and chemistry, and we would like to go beyond that in the sense that we would like to keep the connection to quantum mechanics and statistical mechanics in making modeling predictions. And so in this sense, we would also like to clearly mark the distinction, and we have a causal relationship that really tells us what is input and what is label. And so here I put Schrödinger's equation and your Boltzmann average for some macroscopic observable. Now, I think this is very important because if you think about the history of science, there is, of course, first the experiment, and then theories that have been developed over the long tradition of science in our field in particular. And then at some point you had a new pillar in terms of what was possible for simulation and computational power. And I think what we now experience is the emergence of a fourth pillar in science, that we, thanks to theory, experiment, and simulation, we have the data and the means to build statistical surrogate models, which allow us to bypass the need to solve computationally demanding problems. Right? And so this is, in a nutshell, what I think summarizes the advantage of the field. So when traditionally your error in your predictions due to force fields, semi-empirical methods, mean field methods, starting with Hartree-Fock or going for density functional theory, you have typically an improvement in accuracy. Going to perturbation methods or explicitly correlated methods, traditionally you would have to pay more and more in terms of compute power. Now we can supplant this compute power by training examples, and once you've trained on sufficiently many examples, you can make query predictions in milliseconds at that prediction power. And this sort of linear decay of your prediction error with training set size is actually not made up. This is on a log scale. Your error has to be linear, because it was shown by Wapnick and others that the prediction error of support vector machines, and later also in this paper by Muller et al., it was also shown for neural networks, that the leading error term here is inversely proportional to training set size, and hence on a log scale this must be linear. Now things will get really bad if you start going beyond just sort of fixed configuration, single point calculations. We want to relax the structures, we want to run molecular dynamics, we want to study phase diagrams, we want to do much more than just solving the electronic Schrödinger equation for a given configuration. And so what this would traditionally impose in terms of computational burden was completely unreasonable, even if it was as cost efficient as a density functional theory. And so the hope is that with this fourth pillar, we can finally actually get to tackling extremely relevant and extremely interesting properties and systems. So let me tell you a little bit how I got into this. So in 2011, I organized a long program at the Institute of Pure and Applied Mathematics at UCLA on the topic of navigating chemical compound space for drug and materials design. And at this program, there was my long-term collaborator, Alex Tkachenko, who is now a professor in Luxembourg, Klaus Robert Müller, who is the chair of machine learning at TU Berlin, and his postdoc Matthias Rapp. And we asked this question: if we cannot use machine learning to infer quantum solutions throughout chemical compound space. And what Klaus suggested was that we use something called the support vector machine, or kernel-rich regression. Here you see such an expression. This would be the prediction model for a new molecule or material. You predict its property by simply summing over its training instances I And every training instance gets a weight, the regression coefficient alpha, which carries the unit of your property, and it multiplies a similarity measure of your query compound to the training instance. And there's a closed form solution for your alpha in terms of inverting a kernel matrix. This kernel matrix is the similarity between all your training instances. It could be regularized if you have noisy data. And you multiply that with your reference properties. So this kernel matrix means basically we make a matrix out of chemical compound space, right? So you can imagine chemical compound space looks something like this. These are high-dimensional points, right? In this matrix space, each point is a chemical, and then the question is, how do you represent each chemical? So how do you measure the distances on this high-dimensional simplex? This was a question we were pondering at the time, and then I suggested this atom-by-atom matrix, which is now known as the Coulomb matrix, which encodes the nuclear repulsion on the off-diagonal terms, and on the diagonal terms you have a rough estimate of the energy of the free atom. So very basic. It obeys the physics you would like to see, as all atoms dissociate. The Coulomb matrix then as off-diagonals elements going towards zero, and the trace of the Coulomb matrix would be an estimate of the total energy of that given stoichiometry. Now Alex, he did a couple of DFT calculations then for a data set which we had extracted from this GDB library I mentioned earlier, and Matthias then inverted the corresponding kernel matrices, and then lo and behold we saw the prediction error on the atomization energy decay as training set sizes increased, and that got us pretty excited, because at 6,000 or so really a very small number in comparison to everything that's possible, as I mentioned before, right? Only after 6,000 molecules, or already after 6,000 molecules, we had a prediction error which is sort of on par with the error a GGA density functional would give you for atomization energies. Right? And so that is interesting, but what I find even more interesting is the systematic improvement with training set size. So much has happened since then, and of course there are also other machine learning efforts going on in quantum computing, also for potentials, for force fields, and so the entire field has profited a lot from this and other developments. And just last year, together with Kieran Burke, we did a little retrospective on a decade of machine learning, and this is the number of papers being published in the field, and it's really, I think it's very exciting to be in this field and to join it. I think this is really something that looks very promising. What I would like to tell you now is a set of recent papers that we published. They all came out this year, and in particular, we used machine learning to look at free energies of solvation in particular. We try to predict the structure, the 3D structure of molecules and also solids. And we also used machine learning to try to predict chemical reactions, in particular reaction barriers. So relative reaction barriers of competing reactions, they should determine which compound is kinetically, which product is kinetically favored. Now, all of these things we do throughout chemical compound space, right? So in all the examples I will show, we've trained with different compounds, and then we use the machine learning model to predict these properties for new out-of-sample compounds that were not part of training. Okay. So here you see a plot of a learning curve, a little schematic here. So the challenge often is your error decays, right? You do things properly, but you don't have enough training data, right? So you need to find a machine learning model, or you need to improve your model such that within the training data you have, you reach an accuracy you want. What you want to avoid, of course, is a machine learning model like this. This is typically what you see for parametric models. They level off, and if you're unlucky, they level off above your accuracy target. And what you would really hope for is some way to also improve the slope, not only the offset. Right? So having this in mind, right, we wondered how can we tackle free energies, and in particular we picked free energies of solvation since there was actually an experimental data set on this, and what intrigued us was something that is displayed in this figure, which also comes from the paper. If you take a constitutional isomer, so let's say you have this molecular graph, there are many different conformers, of course, you could use. Now, if you use the continuum estimates for solvation energies, right, the question is which configuration, which conformer would you take? So we generated many conformers for each of these constitutional isomers, and for each conformer we evaluated the continuum solvent estimator, common continuum solvent estimators from the literature, and we see that the free energy of solvation then varies greatly depending on your conformer, right? So for this one, it's the most pronounced. You can go from -10 to -6. And your free energy of solvation depending on the conformer. And so the proposition is then, okay, we should include this conformational information as well. We can, it's not good enough to just have like a single point calculation, and we would like to, this of course obvious from statistical mechanics point of view, but in terms of machine learning, it's not clear how to build such a model, right? So your StatMech average would of course include that phase-space integral. And what we did then was to run molecular dynamics on each constitutional isomer. And so you average over all your different configurations as a time series. And that average then could be a better structural representation than any single configuration. And so for any isomer A or B, you would average their coordinates, and then when you have a query, you also have to run MD on your query, but then using that average for the query, you might be able to have the right representation to infer the free energy of solvation if your model was trained properly on your training data. And so for training data, we took this free solve database from Mobley and Schertz and others, and unfortunately, there are not so many molecules. There's, I think, a little bit less than 600 molecules or so, but it's an experimental data set. And we then went ahead and trained. So for each of these molecules, we ran molecular dynamics to get their average representations. We constructed the kernel matrix, and we took the experimental free energies here as labels to get our regression coefficients. And for testing then, for the prediction, you had to run first the molecular dynamics run on your query, and then you can use that query, that averaged as an input here for Q as an input to predict the free energy solvation for that query, right? And so what you see now is the prediction error that you would get for the free energy of solvation for new out of sample compounds as a function of training set. And the model I just described to you is the FML model, right? So this is the average one. The QML would be using just a single configuration, but it's not clear how representative this is. And for the larger training set sizes, you then see that FML becomes better than QML, which is encouraging. Also shown here are many other state-of-the-art methods. They all perform worse. So this FML is really the most appealing. And also on the scatter plot, we show for out of sample prediction, molecules. We show a scatter plot of FML here, as well as other solvation models in the field, and it's hardly distinguishable. So FML is on par with these legacy free energy of solvation models, and many of them took decades to develop, right? While our model was just trained, and basically once the idea was conceived, it was very straightforward to construct and train and use this model. So how did we use it? Well, one thing we can do is to run it over QM9. QM9 is a data set we published in 2014. It contains also from the GDB, it contains 134,000 organic molecules and their structures. And so for all these molecules, we predicted now free energies of solvation using our model, and you can interpret this distribution in chemical compound space, right, of free energies of solvation. So the more polar one here, they are of course the extremes, and the least polar ones are basically repulsive. You can ask simple for simple descriptors such as hydrogen bond donors. There are simple correlations of the predicted free energy of solvation, and which you might expect here, or number of NH-OH bonds, or oxygen atoms, or number of heavy atoms. So these are all things you can do now. Once you have a decent model, you can extract these simpler relationships in chemical compound space, which might be helpful for experimental design purposes or other problems. Now let me come to the second paper, where we reconstructed 3D coordinates. Now, traditionally, you would have to use the energy to identify structures, right? So the equilibrium structure of a system, we associate that to an energetical minimum, right? So starting with some guessed or random initial coordinates, in principle, you'd shift the coordinates until you find some minimum, and the gradients are 0, and all frequencies are positive. Now, we wanted to see if we can machine learn that map, the map of the geometry relaxation, right? So not only the energy, but so the energy is implicit in this model. In the training data, we already have encoded the information about what should be the geometry of the system. And the way we did this was by making a model where any constitutional isomer set could be dealt with, right? So basically the stoichiometry of your system should be fixed, but for a given stoichiometry, you can then construct an atom by atom matrix where in the off-diagonal terms you record the distances between all atoms, right? Now we ordered these distances by their magnitude, so the smallest distances come first, and then we machine learned each and every one of these off-diagonal elements. So for all these off-diagonal, for each element, you have a different machine learning model. They're basically independent machine learning models. And in this paper, they could still be combined somehow, but we haven't done that yet. If you do this, you can actually construct a model then, which after training, so you train by using different representations for predicting each of these off-diagonal elements. You train this, and then when you predict, you input a graph, right? And based on this graph, the machine will then, for every atom pair, it will predict the corresponding distance. And once you have that distance matrix predicted, you can attach the hydrogens. It turns out to do this without hydrogens is much easier. Once you have the heavy atom framework predicted, you can attach the hydrogens, and then there's a simple algorithm that spits out the 3D coordinates. So here you see learning curves of root mean square deviations in angstrom for different sets of constitutional isomers. This is the C702H10 set. And you see here for different input representations which we used, you see the error coming down systematically with training set size again. Now we stopped at this, in this case, we stopped at this number here because we basically ran out of data. But in principle, you should be able to add more molecules if you wish. But we already reached the sort of accuracy you would expect from legacy codes like this ETKDG or Gen3D, as they are, for instance, used in cheminformatics tool sets like RDKit. So they are physics-based, basically using universal force fields and the energy. And our method is just data trained, right? The C7NOH11 is similar. You see an improvement. And now what's really appealing, I think, is that because it only depends on data and interatomic distances, you can also apply it to tricky electronic situations. For instance, we tested this on the Cabines data set, which we published last year, or some transition states, which you can also predict and which we also published last year. So you see there's a lot of versatility. So for these latter examples, you would not have universal force fields you could apply. You would basically be forced to use a higher level quantum mechanics to do this. And also here, the machine learning model is applicable. This also works for solids, of course. So we tested this on the Apasolite data set. This is a set with tens of thousands of inorganic crystals in the cubic lattice, which is made from quaternary. It's a quaternary mixture of the elements. And you see here unit cell length, pairwise distances, and the RMSD on the entire unit cell. Here's an analysis, so predicted intramolecular distance distributions versus reference distance distributions. You see this looks very encouraging. And we also, what you see here, this is quite interesting. This is the error for each of the machine learning models as a function of where they are in the distance matrix. And I told you that the shortest distances come first. So here our error is the smallest. And this is intuitively, one can understand this intuitively. For the short distances, you have these covalent bonds, and they are very rigid, right? And so it's easy to predict them. But for the long distances, you have very shallow modes where the distance can vary greatly, but the energy hardly changes. And so this implicit distance to energy map does not work so well. And so the error, your regressor will perform worse on those modes, right, on those distances. So that's how we can explain these trends. Now, when we published QM9, there was a whole set of molecules, roughly 1,000 or 3,000 molecules or so, for which the common geometry relaxation algorithms and quantum codes would not work. And these systems would not converge, even though their chemical graph looked very reasonable. And so these were sort of unstable molecules which would dissociate, and we didn't get them to converge. And my postdoc at the time, Raghunathan Ramakrishnan, he is now a professor in India, and he just published this paper here in Chemical Science where they troubleshot these difficult molecules. And we also then in our structure prediction paper wanted to see if we can also with the machine learning model tackle these compounds. And indeed, for many of them, we could also make predictions. And here you see the two predictions superimposed, and they look encouragingly reasonable, I would say, right? This one is the worst, but these others, in more or less, the machine learning model is doing pretty fine, even on these very difficult systems. Finally, I'd like to tell you about our effort to predict activation energies. And what you have here, what we started out with, is a reactant, a simple scaffold of 2 carbon atoms, so about this single bond here. And we have a leaving group X and an attacking group Y, right? And Y can either attack this hydrogen in order to lead to an elimination, or it can directly attack the carbon in order to lead to a substitution. And we now varied the substituents R1 to R4 in order to generate a large chemical compound space. And in total, there's something like 15,000 possible reactants, but unfortunately, the transition state search only converged for a smaller set of them. And so we wanted to see if we can use machine learning to complete the set and to answer questions. For example, what is more frequent? Is it elimination or substitution in chemical compound space? Or when does Hammond's postulate, right? So the idea that the barrier height correlates with the amount of distortion. How does it hold throughout chemical compound space when you look at larger numbers? So these were questions we wanted to address. So the data set was published in Machine Learning Science and Technology in 2020. We used MP2 as well as CCSD to make some reasonably accurate predictions of transition states and activation energies. Here you see some statistics on the data set. So these are distributions of barriers at various levels of theories. And these are the distributions of the transition states for E2 and down here for SN2 in this data set. Now, we trained machine learning models, and you see this up here on the activation energy for E2. And here you see the prediction energy coming down systematically for various representations, which we published previously, or one which we also included, which is this one hot encoding. And for SN2, you also see learning curves, and we guesstimate that at 3 kcal/mol or so, you have the accuracy of MP2. And so this is a threshold which you would certainly like to reach. And so for 400 compounds in the case of E2, or for something like 800 compounds in the case of SN2, you would reach, roughly speaking, MP2 accuracy. Now, with one hot encoding, apparently you get the best machine learning model. And this was an interesting finding. If you apply the same machine learning model to the atomization energy, let's say, or the total energy of the equilibrium structures, you would find the reverse trend. So one hot encoding would be the worst representation. Now, we can then use these machine learning models trained on less than 3,000 examples to predict all the remaining reactants which we tried to converge for the data set and which we did not succeed in. And so this is what you see here. We trained on the blue line, and we predicted, or the orange one, if you add everything up, you get the green distribution. And what you see now is on the x-axis, the difference in activation energy going for E2 or SN2. And this is defined such that on the right-hand side, you would see that the SN2 reaction is favored, has the lower activation energy. On the left-hand side, you would see the E2 favored. And from that statistics, we must conclude the machine indicates that roughly 3/4 of the cases in the reactant chemical space would proceed towards E2 and only 1/4 towards SN2. We also tested the Hammond postulate, as I said. So the way we did this was to plot this distortion in the Y to the Y atom and the distortion to the X atom for E2, and similarly for SN2 in X and Y on the same carbon atom, right? So we plot once for dx and once for dy the activation energy. And you see that in SN2, there's a nice correlation with both degrees of freedom, but in E2, the dy, so this axis here, this dimension here is poorly correlating. And basically it indicates that Hammond does not apply. And The reason we believe that this is so is that you have much more freedom here for Y to attack, while in the, basically the angle, if you wish, this angle, the alpha angle here in green, is much more floppy than what you would have for the alpha angle in this case. And so here, basically, the atoms are really very much constrained to this one coordinate. And this restriction might also be the reason why SN2 is less frequent. There are actually less substituents which would fit into this narrow attacking corridor, and that might be the reason why E2 is favored after all. So with this, I'd like to conclude. I think this is a fantastic community to work in. They're very friendly people. It's all open source. There are many codes that are around. There are many models that are published, open access. You have journals such as Scientific Data or Machine Learning Science and Technology, which welcome data sets and also codes. You have repositories like Zenodo or Materials Cloud that store your data for free so others can use it. And even the workflows, that there are protocols now and workflows that automatize these runs, and they make the science much more reproducible than it used to be. I should add that just recently we did a little effort in terms of an outreach thing for something we feel is still missing, and this is basically an online platform. It's called leroli.com. It should work if you want to try it right now. Where you can enter your favorite compound which you are searching, or you can upload it or also draw it, and then you can search for your compound, and then the web server will basically execute some model on your compound. So you can make your models queryable online for the worldwide community. And so if you then hit enter, you will find the 3D structure which you can save or take a picture from, or also modify. With this button here, you will find all the names of the compounds. Just today, we had an update on Leroli, so the selfie string is now explainable in Leroli. So if you want to look at selfies, what exactly they do, you can actually interactively look at more here. You have a whole bunch of things you can predict for your compounds. So for example, if you click on physical chemistry, you can predict these properties based on machine learning models. And also here as an example, the free energy of solvation as a function of temperature. This is the model developed by people in the lab of Bill Green from MIT. So if you wish to have a model, your model here, just let us know. We'd be happy to include it and make it accessible to the world. So in conclusion, I hope I could convey a little bit this idea that the laws of quantum mechanics, or also statistical mechanics, we can build sort of these surrogate models that add on as a fourth pillar to simulation, to statistical and quantum mechanics, and as well as to experiment. Of course, ideally, I view these things as augmenting each other, of being synergistic, and not they are not out there to displace or replace each other. And I hope I could also convince you about the value of these learning curves. I think if your machine learning model does not improve with training set size, then it's not really a machine learning model. So to us, these learning curves have proven to be extremely helpful. And so if you ask me if this is an evolution or a revolution, I think this kind of control of accuracy, which we have by virtue of these learning curves, together with the speed up of these simple functional forms, this combination, I believe, warrants to call this a revolution. I should also let you know that I'm the editor-in-chief in this Machine Learning Science and Technology journal. This is a journal which is not for pure machine learning. It's not for pure chemistry or atomistic simulation. It's sort of in between. And so if you have some new machine learning model or a machine learning model applied for the first time to something, or some data sets or some code in this domain, this is an open access open access journal published by the Institute of Physics in the UK. So please consider submitting your work there. We also recently guest edited a book and the lecture notes and physics on this topic. And with this, I come to thank my group. So people whose work I presented as Dominic Lem and Nick Browning. Nick Browning recently, with a former PhD student of mine, made me the first hybrid academic biological grandfather. Jan Weinreich, Guido von Rudolph, and Stefan Heinen have also contributed to the work I just presented to you. I acknowledge funding from the ESC and Google and the Swiss National Science Foundation. And finally, I'd like to thank you for your attention, and I'd be happy to answer questions.